Allora, Jenny. Okay. We start? Okay. Good afternoon, everyone. So we'll start again with this event dedicated to the presentation of the National Research Center in High-Performance Computing, Big Data, and Quantum Computing. Before starting, we would like to give you the greetings by our president with a video he registered a few days ago.
Good morning, everybody. It's a pleasure to be here, even if in video, to present the activities of the National Center for HPC, Big Data and Quantum Computing, which was founded and financed by the Ministry of University and Research through the Next Generation EU Italian program. I am particularly glad to participate to this expo in Osaka, which is focused on the design of the future society for our lives, because the activity of our center is really very close to this topic. I remember the first time when we started the project, it was in the occasion of the previous Expo meeting in Dubai. And there we were discussing on how to organize all the activity, on how to invest the budget, which were the fundamental part and which were the main goal of this project. At the end of 2022, we had the inauguration of the National Center. And it was just a few weeks before the launch of ChatGPT in the world. This launch was really changing the world and launching the AI in our society. Since then, it passed more than 3 years, and many things happened, both at the international level, at the economical level, at the political level, at the scientific level, and at the technological level. And after 3 years of activity, we are almost close to the end of our project. And I think this is a natural trajectory and a natural place where to present the result of our activity. Then I hope that you will understand the importance of our National Center, what are the goals, and what will be the impact on our society. And I hope to be again in 3 years at the next Expo version to present this impact on the society and see where we are in this world which is rapidly changing. Thank you very much.
So, okay. Now we move from a general presentation of the activity of the center made by myself, and then we move to 4 presentations dedicated to 4 different domains that we have in the center, dedicated to different research. So let me start with the motivation, why we have this center, why Italy is investing in this. It comes down 4 key reasons. The first one is that this center will accelerate our scientific discoveries and help us innovate faster. And think about, for example, new medicine or better materials, all powered by advanced computing. The second reason is that it will enable us to make smarter decisions using big data. And this applies to everyone, from a researcher making new findings, for example, or businesses understanding the customer, or even industries becoming more efficient using big data. The third reason is that having our own strong center will reinforce Italy's independence in these important digital technologies. This means that we don't have to totally rely on others for crucial computing power and knowledge, of course. The last one is try to bridge the gap between research, innovation, and the market application. So we want to have the results of the research living outside the labs when they are created. Where the money comes. So the funding comes from the Italian National Recovery and Resilience Plan, and thanks to our Ministry of University and Research, we had 320 million to create this center in the 3 years. And there is one main point, as I already said. We want to move from the research to business. So how we use this money? In a strategic way, we are investing half of the budget in the building of the computing infrastructure or the upgrade of the existing one, and the other half of the budget has been used to create the ecosystem. So we invest money for supporting the staff research and the activity, for recruiting personnel, for funding of innovation project, means project in partnership, private and public partnership, or also through an instrument called cascade funding. We invest money to projects proposed by institutions external to the member of the center. Just to give you a few numbers, we have in the center more than 1,500 research staff, and we already recruited more than 270 new researchers and 330 new PhD students. So, which are the main objectives of the center? Mainly two. The first one is to create a national digital infrastructure for research and for innovation, so for public and for private, starting, of course, from the existing one. So we are not starting from scratch, from zero. And what we want to do is to evolve toward a cloud data lake model, easily accessible by the scientists and by the industrial communities, through a flexible and uniform cloud web interfaces. The second main objective is to create the ecosystem. We want to create a sustainable and globally attractive ecosystem based on strategic public-private partnership, since, as I already said, we want to move from the research to business. How we can do this? We have 5 key pillars corresponding to 5 main activities. The first one, of course, is the building of the infrastructure, but we are not talking about only of computing infrastructure, but also living lab, which are particularly laboratories that we are building across Italy to test a new technology in a real-world environment. So they are dedicated both to the research and to the industrial component. Second, we want to set up a center of excellence with a team of high-level experts to develop domain-specific applications. We have 11 different domains. We want to create a strong link between academia, industry, but also public administration. We are focusing also on the education and advanced training for the next generation of data scientists and also managers from the industry, because to become them experts in the digital transition. And last but not least, we are trying to implement structural measures for innovation and for the dissemination of the results outside the center itself. Here is a slide to show you which are actually the partners of the center. So we have 25 universities across the country, and 11 national research institutes, and 15 private partners. Most of them are big companies in Italy. We are also thinking about to open, to include the new members in the center, and also to create international agreement for collaboration with different countries around the world. Here, I will show you the organizational structure of the center. So we have a structure called hub and spoke. There is a central hub dedicated to the management of the center, and 11 spoke. Each of the spoke is dedicated to a different domain. Plus, we also create a transversal research group dedicated to the social impact and ethic impact of the digital science. The first spoke, Spoke 0, is a transversal spoke. It is totally dedicated to the building, the creation of the infrastructure. The other 10 spokes are thematic spokes. 2 of them, you can see the number 1 and the number 10, are in a different color because these are 2 spokes dedicated to the technologies of the future. The spoke 1 is dedicated to the designing future technology for the high-performance computing, and the spoke 10 is dedicated to design technology and software for the quantum computing. The other spoke, from 2 to 10, are dedicated to developing advanced application in 8 different domains. Here, there are few highlights of the application of each spoke. Of course, the program of the spoke are really big, so I will not go through all of them, and I will skip comment on the 4 spoke that we'll present later. So I will just give you a few hints about the other spokes. So spokes 1, dedicated to trying to design a new technology for the future of the ICSC, is trying to create technology that will be energy efficient. And they are applying right now the development of hardware, but also software, to different sectors, like, for example, automotive, aerospace, and also finance. I will skip spoke 10 because it will be presented later. I will move to the other spoke. So spoke 3 is dedicated to astrophysics, but they are using the technology and the software that normally we use for researchers for processing satellite data in application related also to health monitoring and application for environmental and security. Private companies such as agriculture, insurance, or also energy will benefit from this APC-driven innovation. Spoke 4 is dedicated to the health and climate, and they are developing an advanced health system models, integrating HPC, big data, and also artificial intelligence to enhance the climate simulation and environmental monitoring. I will skip spoke 2 and spoke 7, dedicated to the fundamental physics and materials molecular science, since they will be presented just after me. And I will move to the other 4 spokes. So spoke 5 is dedicated to environmental and natural disaster, and they are developing a digital platform for disaster mitigation. And the platform is already in place. They are integrating real-time data analytics from different sources also to try to enhance emergency response strategy. Spoke 6 is totally dedicated to engineering in different domains. And right now they are developing simulation, fluid dynamics in material science advancement and structural engineering, and working with industry like the aerospace and automotive and energy one to create software for enhancing their production. I will skip again Spoke 8 because it will be presented later. I will move to the last spoke, which is the Spoke 9. It's totally dedicated to the digital society and smart cities. They are creating digital twins of cities, so model in ICSC of the cities. For example, they are trying to optimize the urban mobility partners, which means simulate the citizen movement, the traffic flow, and the crowd behavior in real time to try to enhance the urban planning sustainability on the city. So the headquarters of the center is in Bologna, and this new environment, the big data technopole. And here we have the two main infrastructure of the center. So the Leonardo supercomputing, hosted by Cineca, and the Tier 1 of the Italian National Institute for Nuclear Physics, inaugurated 1 year ago. These are already in place, but we are upgrading this infrastructure. So right now, we are working to upgrade Leonardo and to upgrade the infrastructure of the INFN. In the meantime, we are also working to build there two quantum computers with two different technologies that will be ready, I hope, for the end of the year or the starting of the next year. We have a lot of results, but I want to mention just one. So this is an honor for us to have this result. Last year, in May, we had the inauguration of the first superconducting quantum computer entirely built in Italy. And with 24 qubits at the University of Naples. I do say this is really a great result for us and for the country. And moving to the future, we are already thinking about the next machine. And thanks to the Italia project, funded by the EuroSPC, so the European Commission, we are planning to build a new exascale computer dedicated to the AI application, and it will be hosted again at the Technopole. So this machine is 10 times more powerful than Leonardo. And thinking about the environment, so what we call AI factory around this machine, we are thinking to offering something that we call one-stop shop model. What this means? This means that all the environment is distributed around the country, but in some ways intercorrelated. And we want that the community, the Italian and the international one, could have just one point to enter the system, asking for services, asking for collaboration. And this is what we call a one-stop shop model. Here in this slide, you can see which services and what we want to do for the AI factory, but we want to do the same also for the ICSC big data and quantum computing environment. So we became the one point, the single point in Italy to assess our service, our research, our collaboration with us, knowledge. In the same way we are doing for the AI factory. And this is my final slide. It's just a summary of all the points and all the different thing that we have in the center, and what we want to have in the future is to integrate this ecosystem, all this action, all the spoke, and in a better way that we have right now. And so with the idea to position Italy as a key contributor to advanced computing through also strong international alliance and to try to address together the global challenge. So this is my final slide. Thank you for your attention. And if you have questions, no, okay, so let me take the agenda. And we move to the next speaker, is Dr. Tommaso Boccali, from the Director of Research at the Italian National Institute of Thermal Physics and the leader of the sport team.
First of all, apologies for the voice, but this is what I have today. I cannot do more. Yes, but I will also speak about the infrastructure, not only about astroparticle, the astroparticle part. Alessia, how does it work? Play? Okay. So let's start a bit from the infrastructure. Alessia already spoke a bit about this, but it's probably the most relevant part for the project, because we are really putting a lot of effort in building something which in principle should stay long term. It's not something which stays with us with the project for 3 years and goes away. And indeed, it absorbs nearly half of the fundings from the NRRP. Is not only buying new stuff, because this is somehow easy. You buy computers, you put them together, and you hope that they can last. It's also somehow putting together all the resources, or most of the resources which are available before in Italy. So trying to put together new stuff and the existing stuff from the existing computing centers. This is really relevant, and this is the first time we do it, at least in Italy. The second part, which for the future is probably maybe even more relevant, is to try and form a cohort of young researchers who understand how to work with big systems. So they have access to new technology, they have access to training facilities, they have access to supercomputers, we said, artificial intelligence facilities, data analysis facilities, quantum computers, and then they hopefully will either continue in research in Italy or move to the productive system, which is one of the aim of the project, as Alessia said. And third one, and maybe this is a little more long range, we are building something which in principle should be, Alessia called it one-stop shop. I call it go-to point. So whenever in Italy, in the next year, someone, public productive system, public administration, will need large computing resources, large computing experience, we would like to be the place where they come at first and they ask for counsel, for ideas, for collaborations. So how do you build an infrastructure? So clearly you have to buy computers, and that's clear. But that's not enough, because if you buy a computer in Veneto and a computer in Sicily, it's not really helping a lot unless they are well connected. So the part which is really relevant from the infrastructure point of view is the first box, which is the networking, trying to deploy dark fibers at terabit level among all the public and some private centers in Italy. Italy, you know, is not so big. It's 1,000 kilometers north to south. So if you have this kind of bandwidth, latency is not so much. So you can really hope of using resources in Sicily to analyze data in Veneto, or vice versa. So this is our aim, if you want. So this was already happening, has been improved with the project, and you probably don't see it from the colors, but for the first time, islands were reached. Reaching islands is not so easy in Italy, and usually it's the thing which happens last, and somehow happened here. Then clearly you want resources, and you start from something which is already big, because the Leonardo HPC system was already present before the NRRP, but this is being improved in two ways. First of all, a specific AI-optimized system. You know, our center was born in 2022, I think just 1 month around when ChatGPT went out. So the world has moved. Now AI is really important, is on everyone's task list. So this new system with more than 160 nodes has more power on the AI point of view than Leonardo, let's say, even if, for example, for a P64 is probably less powerful. And then you go to quantum computers. Well, the center, as you heard, attacks the quantum computing problem from 2 points of view. There is the research side, and Paolo will speak about it later, but there is also the attempt to try and move it to production level. So move it to real researchers who have a real or realistic problem. They want to have a machine on which to try and deploy it. Initially, this can be an emulator, but at some point, that should become real hardware. And two systems, one by IQM, which is Finnish, and one by Pascal, which is French, are commissioned in these days, are procured in these days, and will be commissioned by the end of the project. And then you have a third field. You have network, you have supercomputers, but you have everything else. Everything else today is mostly the cloud. We have cloud systems from institutions, private clouds all over Italy. They are separate. What we want to do, and this is our ambition, is to try and put everything together, to have so a single software layer, a federation software layer. This is what Alessia called the data lake, which in principle a user has to interface to, and then the user can use HPCs, clouds, quantum computers in as much as transparent way as possible. And this is a software layer that the center has in its project. Most of the cloud resources which are present by now in the center are those from the INFN high throughput computing centers. Just to tell you, these are basically the resources which are used to process CERN data. So these are particle physics resources which are put in common with all the other centers. So yeah, as said, it's not that we started from scratch and we just bought 150 million of resources. We started from Cineca, which is a long-standing HPC center. It was hosting Praise. Praise is the European was the European funder for HPC systems. It was hosting systems of the top level, tier 0 level since long. And Leonardo, indeed, as said, was number 4 in top 500. Now it's become, I think, number 9. Then there is the private sector. Any HPC 6 has ranked 5 in the last top 500.org. But then Cineca before this had the Marconi A1, A2, A3, Marconi 100, Galileo. So all these machines are partially still available, partially dismissed, but they form a long story of experience. INFN, as said, is one of the main stakeholders of CERN computing, and as such, had deployed 11 centers since, I think, 2004, something like that. So these centers are being evolved and put in this data lake. And if you want, this is the distribution of the INFN centers. But as Alessia was saying at some point, now we have a big center. This is this Technopole in Bologna, which is becoming the center of activities of this project. Well, this I probably can skip. This is a list of what Cineca is deploying today. And notably, you see this AI factory, which is over there, which Alessia just referenced to. We got this 430 million euros, I think it was late December or so. So they should be deployed, well, early 2026, I hope. But, I mean, things are moving fast here. We are 4 months from this AI factory, and now people are starting to think about another factor 10 more. So 3 to 5 billion systems to be deployed. And this is one of the first statements by the renewed president in Europe, von der Leyen, that we need to push for this thing, and clearly all the nations are trying to gear up and see if we can have this thing, which will be quite a different system because they need more partnership from industry and not only funded by the public system, but still, well, let's see which countries are really able to put in place this kind of resources. This is, as said, the INFN initial deployment of resources. We bought, okay, here are the numbers. I don't think they are so relevant from this point of view, but huge resources are being installed in the cloud, and this is, again, available to all the center utilization and beyond, because, again, this center wants to be somehow the focus point for all the activities in Italy. We also have a less common system, but they are, for example, in particle physics, becoming more relevant. And then we saw that there is larger interest also from other domains, which we were not clear about. For example, we have FPGA systems or mini supercomputers, which in principle can be deployed close to data sources. Think of industrial utilization or medical utilization. For example, there are these things which can be moved close to data if there is the need, for example, of data security or data locality for some reasons. And you see, putting all together, now the bubbles and the boxes are becoming huge, and there are many systems, probably more than we can remember by heart without looking into a map. Just to give you, okay, I don't want to go into the gory details of this thing, but just to tell you which is our idea of a data lake, for example. Assume that you are a user. You need to process large data sets with lots of computing, because I don't know why. Either you get data from a satellite, or you get data from an industrial apparatus, or whatever. Our idea is that using this thin middleware layer, which is by design done only with the open source software. So it's something which we can deploy without problems in any location. And this comes from the experience of particle physics, but more, not only this. In principle, this user, with the epiphase over there, can submit workflows, and then some system, some smart system will decide if using a supercomputing is the best choice for this, or if it is better to go to a specific site because, for example, it's closer to data. But all of this with a single authentication and authorization system. So the idea is that you don't have to have an account on Chineke, an account on INFN, an account on something else, but with a single account, you have access to the full system which is deployed by this project. This has already been prototyped, and we hope that it will be made more real, more solid by the end of the project. So, okay, this is the part about the infrastructure. Now, let me spend another 5 to 10 minutes about the things I really do, because as Alessia said, I'm a spoke leader of a spoke called Fundamental Research and Space Economy, which is the number 2 signed over there. And we clearly use a lot the infrastructure, and I wanted the infrastructure I just described, and I just wanted to tell you, for example, which are the groundbreaking things that you can do once your researchers, your collaborators are given this kind of resources, this kind of capabilities, because they were simply not present before. We, as a community, are experimental, theoretical, high-energy physicists, nuclear physicists, particle physicists, but we have also people working in gravitational waves, which is becoming more and more important in the physics realm. And for example, physics of complex system. You know, Italy with Giorgio Parisi got a Nobel Prize a couple of years ago, or maybe it's more by now, about this subject. So altogether, what we do here? So the idea is not to do science per se. The idea is to build tools which enable researchers to do more than they are doing today. For example, using the resources that the center is is making available to these users. We are a subset of the full collaboration, but as you can see, a big subset. There are really few boxes which are not colored. It means that our spoke is quite big. You have to scale down the numbers Alessia gave, but in practice, we are hundreds of between staff researchers and hired researchers and PhDs. I clearly cannot go and describe what we do in 5 minutes, and honestly, it would be also very boring. Let's just select a few things just to show you what we are doing. We go from theoretical physics, for example, a new program to calculate Feynman diagrams was prepared, and it's made available to the public. This is from the theoretical side. We do gravitational waves, sorry for the typo analysis, using some modern techniques for continuous sources. Continuous sources means you don't search for black holes collapsing, but something which stays with time. In general, we prepared ways and pipelines to analyze quasi-interactively large amounts of data. So the dream is you do on your laptop an analysis on 1% of the data, then you just click a button, and this workflow gets spread to HPCs without you changing anything, and you get the result in minutes instead of days or even more than you do today. So a transparent way to increase the processing available to the researchers. We do simulations on dark matter, but not only about physics, because, for example, we have researchers working on cultural heritage. For example, trying to understand and learn generative adversarial networks from paintings. So try to understand and emulate how a given painter was working, or even more. Given that you understand how a given painter was working, if you get a damaged painting, you can somehow restore it, because you can imagine how the painter would have done the part that you are now missing. Or even in the satellite image analysis, for example, as you know, there are diseases which are destroying vineyards, which are very important for Italian economy. Just try to understand from satellite images which are the areas which are more hit by given disease, and so that you can much faster try and find a solution to that. Okay, that's about research, but what about industry? It's not a trivial question, because once we started preparing this project, we were really a little puzzled. So, okay, we find the Higgs boson, we find gravitational waves, and so, but does the industry care? Can we find a way to communicate and work with the industry? Well, in the end, if you abstract a bit from the data you use, so you abstract that the data comes from a collider or from a given device, in the end we treat large and distributed data sets. We process them on distributed heterogeneous platforms, so FPGAs, GPUs, CPUs. We, by now, use artificial intelligence everywhere, being them images, graphs, or other transformers, or other technologies, and we develop and maintain complex software stacks, so millions or 10 or millions of lines on code. And in the end, when we made clear that this is what we are able to do, we could find quite easily interest in the industry, because in the end, they do the same thing. It's probably on different data, but the needs are the same, the technologies which can be used are the same, and in the end, if a solution can be deployed on our systems, they can happily try and use it. They do large data analysis. For example, think of satellite images. They are pouring data at a very fast speed. Again, in satellite images, you have to do image analysis to understand features, to understand diseases, to understand whatever pattern you're interested to. And then also, the industry has the need to try and to be able to scale from their little computer that they have in a corner in the room to a big system the day that they will get more data or are interested in doing more processing. For example, this is a very short list of the industrial projects that we have active at the moment. First one is simulation of oil field characteristic, basically trying to solve the partial differential equation governing these fluid systems with machine learning, which is, if it works, much faster than standard finite element or whatever mechanism. We are able to look into streams of physics data, and in the end, the streams of financial data are not so different. If you have ways to find anomalies in physics data, you can use the same techniques to find a fraud, for example, in a credit card stream. We do satellite data handling with blockchain certification. It's the same what we do in our research every day. Risk assessment in urban areas, for example, looking into images, predictive maintenance, which is again a sort of anomaly search on industrial apparatus, and so on. These projects are all happening. We hope they are going to have real results by the end of this year, the end of the project, but they show an interest in the technologies and the stuff we are able to do. Just closing, a few numbers. In these maybe 5-6 years from the start, we produce 600 papers which positively acknowledge our project. We have more than 150 conference talks, projects for the outsiders. I don't remember if Alessia called them cascade calls or open calls. It is the same thing for external entities. And we are collaborating with global collaborations like Atlas, the LC experiment, but also Bell2 in Japan, here, for example, Virgo, ET, Dune, Kagra in Japan, all these kind of activities. And we organized lots and lots of schools, because in the end, as said before, the second pillar of this project should be really try to put to speed a cohort of researchers that will be able to use this thing even when the NRRP will be done. So I think I can close. The infrastructure is currently, well, when you do this math, you can always make mistakes, so I don't really want to be too assertive, but I think Italy by now is the first country in Europe as HPC resources, probably number 3 in the world. Number 2 should be Japan. I could be wrong. Apologies if it is not true. Internally, we want to contribute to a reference infrastructure for Italy for the next years, assuming that the ministry and the government will allow us to go on with appropriate fundings and appropriate ways. I'm quite proud, maybe even a little surprised, let me say, that we were able to form a link between the academic system in hard sciences and the industrial system. In the end, collaboration worked. There has been probably initially a different language that you had to overcome, but now things are flowing. And I think, okay, I spoke mostly about Italy, but as Alessia said, I think this center is open also to outside. This is one of the reasons why we are here in Osaka. And new collaborations are always welcome, but this I leave to Alessia in case. Thank you. And I could even speak.
Good. If there are no questions, we move to the next speaker, Professor Stefano Fabris, the National Research Council of Italy. He will present an overview of APC-driven research on material molecular science.
So, thank you. Thank you for those who agreed to come here, for those who are connected. We have heard that the structure of this National Center has at the core a large infrastructure, world-class computing, and then is organized in a set of 10 vertical scientific verticals. And my goal here, my duty, is to report on one of them, which is on materials and molecular sciences. So why dedicating a spoke on materials and molecular sciences on this national enterprise? Well, if you think about it, you all know it, that human civilization revolved around the discovery of new materials since the very beginning. And actually, we call the different phases of human history with, often with the name of a material. The Stone Age, the Bronze Age, the alchemists in the last century, or the Industrial Revolution based on steel, of course, the Silicon Age, the digital era that we are living. And so, in a sense, materials are at the core of trying to address the most challenging problems that humanity faces now. I'm thinking about energy, I'm thinking about emergencies on environment, on climate. I'm thinking about space economy. We have heard something 2 minutes ago, quantum technology, but also mobility, but also health or precision agriculture. I mean, every one of these area is related to some critical challenge that we are facing now. And at the end, there is a large weight on the solution of these challenges that are based on the discovery of new materials. However, it's impossible, or it's not modern anymore. You can't think that you can discover this new material in a sort of serendipity approach like it was done in the past, like hoping to try or to discover a new material by chance or by mixing, trying to mix elements or compounds. So we are in a position in which we can, how to say, really employ the extensive computing power that is available today, and you can somehow change the paradigm. You can try to reverse engineer the search for new materials. You try to find materials on the basis of specific properties that you want to have. And so this is what we call the design of novel materials, a new paradigm that is at the core of this POC, so materials design and discovery. In a nutshell, what does it involve? It involves two things. First, be able to solve with the sufficient precision fundamental equations that actually determine and govern the properties of complex materials, not in ideal solutions, starting from ideal systems, model systems, down to realistic applications. And the second thing, even more modern, is to train, based on the big data that are generated with these simulations, to train artificial intelligence or high throughput models that allow to predict new properties, new materials from databases. And so this involves a set of three interconnected ingredients. So you have, of course, to develop new theory, new models. You have to reverse them or apply them and implement them into efficient software. And then you have to design and engineer the software so as that it runs on the most sophisticated and fastest computer available. Which are the general goals? Why do we do this? So of course there's also a strategic and political issue behind investing so much money of the recovery funds on this issue, on these materials. And the first one is start on a fact. Europe and Italy is already in a leading position in the field of software for simulating new materials. So one very first goal is developing technologies that are capable to maintain and even strengthen this leading position. So develop, implement, maintain software technologies that allow the simulation of materials, as I said, in a multi-scale, starting from the electrons down to the mesoscale. These codes must be optimized to the efficient use in terms of simulating accurately the properties that you want to discover and simulate, but also they have to be optimized so as to maximize the efficiency on the supercomputers that become available year after year, that are different one from the other, and that involves billions of integrated funding from European Union, from the national funds. And it's important not to waste these resources by running on them codes that are not optimized. And third, one part of these recovery funds goes under the slogan from research to private enterprises. And so it's really important to try now to make an effort to promote the competitiveness of the country by trying to combine the academic and the private sectors by using the tools that empowers the connection between these two systems. And this is somehow, I will show some examples at the very end. Okay, so which are the areas and which is somehow the path that we want to follow within this journey? So as I said, at the heart of this POC are the flagship codes. So we select and maintain a set of flagship codes on which we have worldwide leaders, and made them available, developed them so that they are available to the scientific and private company communities. Then we have a path on using these codes to generate big data and to use this big data to find new materials. We have a set of activities and a work package on monitoring and improving the accuracy of the methods and their implementations of the results that are generated. And then we have two branches that relies actually on how useful is all this machinery, what we can define of new with these sophisticated tools, and to whom we can make them available. So this is just to give you, again, an overview of who we are and where we are. This is, again, as the previous speaker showed, is a subset of the participants to the National Center. You see they are spread from north to south of Italy. The spoke is led by the National Research Council, but you see there is a good mixture of research institutions and many universities. Another goal and actually result of the National Center was to connect different communities that used to work disconnected. And this is somehow demonstrated by the huge number of staff that is involved and they're working on the same goals within the spoke. So we are almost 150 researchers and about 100 new young scientists that have been recruited thanks to this initiative. What is the impact and the engagement that we reached so far? Essentially, we managed to reach and engage 4 different communities. The community of the software engineers for code development, the community, the scientific community, so all academia and public research institutions, the new generation of scientists working on this area, that is training and education. And finally, this is probably the newest thing for us, for the communities that are involved. We were able to reach and engage with the applied research and the industrial part of development. So let's start with a quick go through between the main activities and goals. So as I said, at the core of the National Center, there is an infrastructure, the Leonardo machine. So Leonardo machine is not alone. This is part of a European effort that was somehow decided about 10 years ago to create in Europe a world-class constellation of supercomputers. So this was a decision, a strategic decision for Europe. In 10 years, we developed, as I say, a constellation of up-to-date, tier 0 supercomputer distributed across Italy. Leonardo was mentioned, is part of it, is one of the fastest, is at the moment the 4th in the top 500 list. But this is not alone. This is only one part. This constellation of supercomputers is then integrated with a set of quantum computer, which is also part of the center, which is then integrated with a new set of supercomputers dedicated to the AI, called AI factories, which is then integrated with a new generation of supercomputing machines dedicated to industry-grade supercomputing, which is then integrated again with a superclass of AI-dedicated supercomputer, which will be called, again, AI factories and again. So this is really part of a multi-billion investment in computing from the European community. Italy played really a major role in this strategy, and we have a responsibility. We have a responsibility of not wasting this money, not wasting not even a fraction of this money, because we are talking about billions. And how do you typically waste money in this kind of application? Is by running codes that are not optimized to the machines that are available at the moment. So you're using thousands of nodes of the machine, and if your code is not able to, it's called to scale linearly, that is to double the performances or to shorten by half the time as you double the number of nodes that you use, then you're wasting money. You run on a very big machine, but you use it only 70% or 60% of the machine that you are using. And so you are wasting 40% or 30% of the investment. So this is our responsibility, and so we need software development. We need software development to fully exploit the computational power, and at the same time, you need software developments to really treat large systems that then allow simulations that are useful also to the real world, let's say, outside the academic community, to industry. How do we do this? We do this by developing, maintaining, making available a set of flagship codes that enhance the performance and the, let's say, overall efficiency of their applications in these machines, so to improve the parallel performance and scalability of these codes, and essentially to implement new features that become available or become are somehow required by the scientific community as the field and research boundary moves on. Which are these codes? These are Italian flagship codes that has an international perspective. The first one is Quantum Espresso. Quantum Espresso is probably the most used code for ab initio simulations in the world. It has thousands of users distributed all over. It is open source, so it can be freely downloaded, freely used, freely downloaded even on the big machines. It's efficient. It has been shown to be able to run efficiently on the most modern infrastructures by using thousands and thousands of nodes. Then there are other codes like Yambo that are somehow more specialistic for excited states of matter, like the states that you have by shining lasers on matter or on molecules and understanding the behavior, even at the ultra short time scale, like femtosecond science, something that was the object of a Nobel Prize 3 years ago. Other codes that allow the calculation of many ground state properties, like of materials, in this case, ordered materials, like which is called crystal, and a set of codes that allow for the very accurate calculation of important thermodynamic properties, like free energy. How to use the big data that are generated by these simulations tools. This is the subject of the second work package. So develop optimized technique for high throughput, artificial intelligence and machine learning in the area of computing. These allow to discover new materials, new drug, and to predict, on the one hand, you can use the data that you generate to discover new materials and drugs, but you can use the data that you generated by running the previous codes on specific systems to develop predictive models based on artificial intelligence that then you can use to treat systems that are much, much larger or to simulate systems for a much longer period of time. And so there are 3 levels here. If you think conceptually, you can use the code to generate large databases that then are something that you can store and you can actually publish and people can reuse. You can use this stored data by developing some workflows to extract models or to extract new data that were not subject of the first investigation. Of course, all this data must be accurate. So it is important to be sure and develop a work program that allow to maintain an eye on accuracy and reliability of your simulations. And this is done by coupling simulations that are used for the real materials, even for industrial application, coupling them with quantum chemical simulation that can reach chemical accuracy. So these involve benchmarking, essentially, benchmarking data or a subset of data against quantum chemistry or quantum Monte Carlo, and this it holds both for ground state calculation or excited state calculations, and the interatomic potential or the new models that were developed or that are developed with the high throughput, the large big data work package. Finally, applications. Of course, you want, at the end of the day, you want to use software tools, software codes, infrastructure to perform challenging simulations to solve practical problems. And this is part of what we have reached. We focused on three main areas: new materials, new functional materials for energy applications. You see here some examples. For example, the photochemistry and solar fuels. Solar fuels means being able to convert directly sunlight and water into a fuel, hydrogen, or with more complex electrochemical reaction, photoelectrochemical reaction, even methane or methanol. This is a very, very challenging problem in chemistry and physics, and simulation really help. Another field is batteries. Actually, this is very timely for this talk, because by developing a program on batteries within the National Center, the Italian government and the Japanese government last year signed a bilateral agreement for a joint program funded nationally from Japan and from Italy, dedicated to the development of new batteries, also through simulations. And so this is something that we are somehow a branch out of the National Center that continues at the international level. Of course, fuel cells, to use essentially the fuels that you can generate photoelectrochemically to generate electricity. Materials for biomedical applications like new drugs or the large field of nanomedicine, precision medicine, and all sorts of applications dedicated to specific technologies, like bio-based photoreceptors, or here are some hybrid materials, or the large area of two-dimensional materials with application, for example, in microelectronics or similars. Finally, reaching different communities. So you can use all the package of the techniques that I've described to reach at least two distinct communities. One is the industry and private sector, somehow using the competences of academia to solve specific problems in collaboration with industry. And reaching out experimental communities working at large-scale infrastructures that collect large amount of data that have often difficulties in interpreting these data. So this part of the project developed and interacted with these two communities and developed specific tools, which maybe I can skip at this level. And I want to turn on something that is probably one of the most precious results of the center, which is the boost on the integration between the private sector and the academic community. This is something that really required a global initiative like the National Center. It pushed a change of paradigm in the way of working of the researchers on the academic side, and a way of asking questions from the point of the industrial side. So we managed to somehow find a playground in which we can develop this change of paradigm, change of solving problems and asking questions. And this is one part of the effort, a set of innovation grants that were used to generate seed projects with the private companies that were part of the national centers. You see, we engaged in probably the largest companies in Italy, like Eni, like Leonardo, like the Italian railways, even some coffee. You have Illy at the stand outside here. We actually work with Lavazza. They are both actually pretty good. This is somehow one set of innovation grants, one set of programs that allowed to somehow test this integration between private and public. But then we scaled up this effort by going open, going outside. We had quite a large amount of cascade funding to dedicate to creating or creating new projects with the communities that were not part of the national center. So we had a call on several type of materials or of applications that we could develop together with whoever was interested. And that was a large success of the project. We managed to get a reply from quite a good number of public companies and other private public universities or centers and private companies. And these, I somehow want to emphasize, this public-private partnership is going to be even more important in the next generation of funding calls. I mean, in FP10, the private-public partnership will be one of the pillars for what it is known up to now. And so this is another somehow goal and result of the National Center, because it trained the country to be ready to the next round of funding that will be available at the European level. So with this, let's say I can invite you to the national conference of the SPOC 7 on materials, if you like, and if you are able to join us in Trieste. This is going to be held next month, and I thank you all for the attention.
We move to the next speaker, Dr. Alessandra Retico from the Italian National Institute for Nuclear Physics. She will present an overview on research in the center on in silico medicine and omics data.
Hello, good afternoon to everybody. So let me start again from this overview of the activity of the National Center. It was reported that we have 11 different sub-projects within this project, and I will report on the activity of SPOC 8, which is dedicated to the use of the infrastructure that is delivered within the SPOC 0 for the medical community. So the research in medicine strongly needs to be supported by high-performance computing and big data platform for data analysis to carry out research in what we call in silico medicine and omic data. And the final goal is to achieve the goal of a precision medicine approach in healthcare. So the participants to these talks are in particular the leaders, Professor Cavalli from the Italian Institute of Technology and Professor Pappalardo from the University of Catania. They are co-chairing this talk. And you can see here a subset of the partner of the National Center that are working on this activity. And of course, we have a research institution and university, and also private company and research hospitals. So the goal is the activity of the SPOC is focused on precision medicine, and precision medicine means essentially a medical approach that tailors the intervention to each specific subject. So in contrast to what is a traditional approach, which is mainly based on the one-size-fits-all approach, so one medication for all individuals affected by a specific condition. The precision medicine approach instead want to target each individual with a specific treatment, and this treatment should be focused and based on the characteristic of each individual. So essentially, in this idea, each person will receive a specific, the right treatment to the right person at the right time. And in particular, this goal, the objective is to achieve this goal, let's say, within this decade. And to make so, we have to improve several research fields to achieve this goal very soon. Because the idea is to account for individual vulnerability in genes, in the environmental factor, and also in the lifestyle. And first of all, we should acquire a huge course of data, of healthcare data, and this course should be also longitudinally collected. So we have to move from cross-sectional studies to longitudinal studies in order to be sure to understand what are the reasons why some pathological condition may arise. Of course, we have to collect data from electronic health records, and also from phenotypic information about patients and environmental factors, maybe using some wearable devices. All these data, of course, should be collected and become big data, the big data generated by healthcare devices. And this big data include a very important part, which are the genomic data. And the idea is that precision medicine can be achieved if the genetic exam are done on a routine based, not only as a second or third level analysis in medicine. So let's say the democratization of genetic exam. All this data will become a huge amount of data, and of course, to mine this data, to process this data, artificial intelligence approach can be very useful. And for this reason, a huge and important computing platform should be built. So here you can see what are the requirements in terms from the infrastructural point of view that are necessary to achieve the precision medicine goal in, let's say, the next few years. So from the point of view of data analysis, the next generation bioinformatics tools and also the structural genomic approaches and the drug discovery, we will see in a while, should need high-performance computing facilities. All the data generated by new devices that are available in healthcare should be collected in a big data storage facility, which of course should be compliant with the current data protection regulation. And computing facilities and data should be also easy accessible to clinical researchers, maybe by means of a cloud platform, which has a good and efficient user interface. The activity of this spoke is mainly organized in 6 work packages that covers 2 very wide areas, such as the in silico medicine and omics data. So I will briefly overview the activity of these work packages, and in particular starting from the in silico medicine approach. So I will talk about digital twins and in silico medicine. And as digital twin, we refer to the virtual representation of a system on the virtual representation of a real entity in general. But if we talk about the human subject, of course, it is not possible to make a precise virtual representation of a subject. We can build digital twins of subparts of a human subject, such as a functional system or one organ, or and we will see some implementation in a while. Within silicon medicine, instead, we mean essentially the computational medicine approach. So all software systems that can, by using maybe digital twins, make prediction about the dynamics of a biological system. In the field of simulation, so in the field of in silico medicine, we can overview very quickly this application that has been delivered by the University of Catania, so the use of the universal immune system simulator, which has been developed to simulate the dynamic of the human immune system, both in the physiological and in the pathological condition. In particular, this immune system has been set in order to monitor the response, to predict what is the response of the immune system to viruses, and in particular influenza virus, and in order to enable the so-called virtual clinical trials. So new drugs can be investigated, and the effect of new drugs on the immune system in relation to specific pathogens can be analyzed. This universal immune system simulator has been customized also in the field of the study on multiple sclerosis. In multiple sclerosis, we have a different form of this pathological condition, and in particular, there is the so-called form of multiple sclerosis that is the relapsing remitting form, which can be treated nowadays with different pharmacological approaches. So in this implementation, different layers representing the different pharmacological approaches have been implemented in the simulator. And this is possible to verify what is the effect of this treatment on a virtual patient. The advantages of using digital twins of patients is very high, because we can simulate thousands of patients. So we can carry out a simulation of this interaction between pharmacologic treatment and patient and virtual cohort of patients. And the system has been validated against 2 real clinical trials that have been conducted recently. And the results that are obtained by this simulator are consistent with the real clinical trials. So this kind of system is, has been validated, it is ready to be used in different autoimmune diseases, for example. In this field of in silico medicine, another approach is the FENSIM, so the phenotype simulator, which is a probabilistic algorithm that can calculate the effect of gene or proteins or metabolite regulation on the appearance of the phenotype characteristic of patients. It is based on data shared in the KEGG and Reactome data sets, where KEGG is the Kyoto Encyclopedia of Human Genome. So this kind of simulator has been implemented and has been delivered on the supercomputing facility, and is now available for researchers to carry out their simulation. Also, the bone strength approach has been implemented in a node at the computer center facility, And it is another instrument that provides the possibility to make in silico trials. And it is very interesting, the fact that starting from digital twins of subjects, in particular the thigh bone of subjects, it is possible to simulate what are the possible side fall of a patient in order to predict what is the probability of a bone fracture. And again, in the, the virtual population of thigh bones has been derived by real computed tomography images of patients, and these data have been sampled in order to obtain a wide population of patients. Also, this bone strength approach has been implemented on Leonardo and Cloud INFN resources, and so it is possible to make this virtual clinical trial and try to predict what is the effect, for example, of heat protector on the reduction of the probability of having a fracture. Another implementation that has been done on the computing facilities available in the National Computing Center is this NetMe software, which is available as a web-based platform. And it is very useful to keep a researcher in the clinical domain updated with the current literature. It is based on the use of the OpenAI ChatGPT chatbot, and especially it takes in input the query by the user, and it is focused on the analysis of gene expression, and it revised the literature, the recent literature available on PubMed Central, so the public database for medical research, and provides the last update about the gene expression papers that have been published. It provides the output in terms of the natural language, so it's very useful and can be customized even to other research fields in the clinical domain. So let me go through the omic data analysis and the implementation of artificial intelligence-based approach. And the requirements for this field of studies is in particular related to the occupancy of this kind of data, because for genomic and omics data, for the exam of simple patients, we can acquire data that very easily reach 10 to 100 gigabytes. And if we add to this data also imaging data, phenotypic data, or environmental factor or of the patients, we have to add more than 10 gigabytes more. Of course, we have large data sets, and so we need also high, powerful computing facilities to mine this data. And in this field of research, it has been developed at Cineca, the omics web interface, which is a user-friendly web interface that allows to upload genetic data, and it allows to analyze this data by using the NVIDIA Clara Parabricks. And so the data are transmitted in a very fast way, and so the uploading and downloading of data is very fast, and the analysis works on a virtual machine. Everything is compliant with the current data protection regulation, and the analysis is very quick because it relies on GPUs, which are available on the virtual machine. This is the interface, the appearance of the interface. You can select which gene you want to analyze, and so it is very user-friendly for the user to upload data and receive in a raw format and to receive the results. The SPOC leaders choose a specific use case to focus the effort of the SPOC on, and in particular, this use case is the research on pancreatic cancer. Pancreatic cancer is also known as the silent killer, because pancreatic cancer is quite asymptomatic in the early stage. And despite the 5-year survival rate increased in the last years, it is quite low. It is about 12%. So 5-year survival rate to 12%. Is something that we have to work on. So the idea of this book is to combine a different omics approach, and in particular to use advanced sequencing technique to identify new gene mutation that can be that can influence disease progression and also response to treatment. And the idea, of course, it's an Italian project, so the focus now is on the analysis of a cohort of patients acquired in Italian institution, in particular the Humanitas Research Hospital, and the data from a cohort of Italian subjects has been already acquired and analyzed, and some genetic variants responsible to the disease were already identified. So the goal is that by using the genetic information, it could be possible to design new drugs and to treat each patient with the appropriate and personalized treatment. So the idea is that omic science is very useful to identify genetic variation and to support the discovery of new drugs. And of course, these two approaches can be combined to develop new treatment in the view of personalized medicine approach. And in this framework, the computational models are extremely important, because when we identify new genetic variants that are related to a specific condition, and new drugs can be planned, can be identified to target these molecular, pathological condition, we have the possibility to use virtual trials to select among all possible drugs can be used in this case by relying also on biophysics, on medical chemistry and biochemistry. We can set some virtual clinical trials that can allow us to choose the most promising approach, and only the most promising approach should then be converted into a real preclinical and then a clinical trial. So there is this is a money-save approach, of course, time-saving and also money-saving approach. This kind of approach can also be implemented not only to discover new drugs, but also to repurpose current drug. And also in this case, if we can use an already approved drug for a different disease, it is of course a cost-effective approach. From the point of view of the computing infrastructure, the genomic analysis, of course, are the ones that can benefit most of the implementation of HPC resources. For example, to run a somatic pipeline, it is needed at the moment to run on traditional CPU resources for 50 hours. Instead, if we use a node equipped with GPU, state-of-art GPU that are now available at the supercomputing center, we can save time, and the same computation can be done in 3.5 hours. So a huge gain from the point of view of the time needed for this kind of analysis. And if we have a look at how omics data appear at the moment, we can see that the analysis of a single gene of the exome are only the tip of the iceberg. Instead, genome analysis, the whole genome analysis, can represent the visible part of a iceberg. Instead, the hidden part of the iceberg can be represented, can represent instead all the other omics. It means metagenomic, proteomics, lipidomics, metabolomics, but also radiomics, which is the computation of descriptive features from different medical imaging devices. In order to all this information should be put together into a unified framework. So we should implement a multi-omic overview of each single subject. So nowadays we have many healthcare systems that can investigate the human subject at different spatial scales. So at the scale of the DNA, at the systemic scale, at the whole system scale. So we have to also to monitor the environment and the lifestyle of the individual. And of course, all these devices produce large amount of data, and this data should be mined, should be stored, should be organized, should be cleaned up, and finally processed and mined. And in order to do so, we need to deliver a solution mainly based on artificial intelligence. So this is the challenge that we have to face nowadays, how to integrate this complementary information coming from different investigation machines. And of course, this integration could help us to understand the human health and disease condition and allow to deliver personalized prevention, diagnostic, and therapeutic strategy. So in order to conclude, I think that I underlined the fact that the modern healthcare system produces really a large amount of data, and in particular, the advent of genomics and all the omics data in general needs suitable hardware and software solution. All this data should be also analyzed in a comprehensive view, and so it is necessary to develop machine learning and deep learning algorithms to mine this data. And the Italian National Center for Supercomputing is actually developing suitable computing infrastructure to serve the scientific community of researchers in the medical fields, and to support this kind of infrastructure can support the development and validation of solutions for precision medicine. Thank you very much for your attention.
Question? One question.
Good morning, Alessandra Rinieri, Medical Genetics, University of Siena. So first of all, thank you for your talk. I think the interaction between geneticists and physics and experts of big data nowadays mandatory. And so my comment and question is related how to really integrate in the real world and how to use this tool in the real world. As as you have shown, now we are using the two main apparatuses, the NovaSeq for short read sequencing and the Nanopore, as you have shown, for long read sequencing, and that the amount of storage for just one patient is 1 terabyte, not gigabyte, but 1 terabyte for long reads. And we are, in the real world, we are managing about 200 patients per week. So this is just for genomics, not talking about omics, that this is the future, because for omics data, we have too much variability right now in order to really to compare each other's. But just talking about genomic data, so if you want to comment a bit more on this topic.
Yes, of course. This problem of how huge are the data from genomics is a very good point, because we know that in Italy you are from a university research center, and of course only big centers such as research center at university can handle within the same hospital such amount of data. Of course, this is not possible in every clinical center in Italy. So something should be put together at a national level as a repository of this data. And of course, it's not up to me to discuss this topic, but from the Ministry of Health, together with the Ministry of Research and other institutions in Italy, it is necessary to plan how to handle this data. Because of course you need to store this data for a while, to retrieve this data very easily. So in this project, of course, we are preparing the platform, the environments according to which one researcher can upload the data and retrieve the results. But how to deliver this system at the end of the project to the community is still something that we have to work on and to think carefully.
Thank you, Irene and Alessandra. And we move to the last speaker, Professor Paolo Cremonesi from the Polytechnic of Milan. He will present an overview of the activity on the quantum computing.
Thanks, Alessia. So let's start to keep an eye on the timing. So thanks everyone for being here. And so today I will give you a high-level overview of what you're doing within the National Center on Supercomputing about quantum computing. So I will give you a very quick overview of the organization of this spoke on quantum computing, and then I will list you the different type of projects we do have within this spoke. The activities on quantum computing are carried out by 15 public institutions. So we have universities, we have public research centers. We have, for instance, CINECA as an example, the National Supercomputing Center. And we have also 10 private institutions that are active members of the spoke. And all the activities are coordinated by my University Politecnico di Milano together with the University of Padova. Within this spoke, but as you have seen also in other spokes, there are 3 types of projects we are carrying on. So we have what we call the flagship projects. These projects are led by universities or public research institutions, which are member of the centers. And overall, we for the past 3 years, we had a budget of, roughly speaking, 25 million euros. We have a second type of projects. These projects are led by industry, so private organizations which are member of the center, and with an overall budget of 2 million euros. And then we have a third type of projects. I'm calling them the external projects. So these are projects led by industries or public institutions which are not member of the center, with an overall budget, roughly speaking, of 3.2 million euro. And all the projects, regardless of the families within this spoke, have been divided into 3, let's say, work packages or research lines. So we have the first research line is about software. So within this research line, we focus our attention on developing applications or algorithms that are able to run on quantum computers to solve specific problems. In the second research line, we focus on compilation, transpiling, and emulation of quantum computers, so all the middleware layer of the quantum computing stack. In the third research line, we focus on the hardware and the firmware, so we focus on how to build and how to operate physical qubits and physical quantum computers. And within the activity of the center, we focused on supercomputing, on photonic technology, and on neutral atoms technology. First of all, I would like to give you some examples of the flagship projects we have been running. So, starting from the software application layer, we have two flagship projects. One is about the design of a platform for the benchmarking of both quantum computing applications, but also quantum computer systems. We have a second flagship project there, which is about the usage of artificial intelligence to support the design of quantum computing algorithms. As for the middleware research line, we have a flagship project which is about the design of an efficient emulator of quantum computers, which is able to support more than 100 qubits in its emulation. And finally, at the hardware level, we have two flagship projects. One is about the development of a quantum computer platform based on superconductive qubits. So by the end of the year, we are planning to release a machine with 60 qubits, and hopefully next year we should be able to release a machine with more than 100 qubits. And as another example of a technology which is a more challenging technology, so we're still working on it, but we are working on a photonic sampling machine with more than 5 photons and 24 modes. We do not have the time to see the results of all of these projects, so I want to give you only very few examples. So I will start from the benchmarking of quantum computer applications. In this project, there is a cooperation between Politecnico di Milano, University of Padova, and Cineca, and we released a web application which is able to compare the performance of different algorithms. In this case, we focused on machine learning algorithms running on quantum computing platforms in order to see the relative performance of these algorithms. And here, the main goal was to, let's say, design a benchmarking system which was easy to be used also by non-quantum computing experts. As a second example of the flagship projects is the design of an emulator, an efficient emulator of quantum computers, which is based on tensor networks. This is a project in cooperation with University of Padova, INFN, and Cineca. And currently, the software can be downloaded. It's an open source software, can be downloaded with an Apache license. Is able to, as I was telling before, emulate more than 100 qubits easily on a standard, let's say, computer. And we are releasing this emulator on the Leonardo supercomputer at Cineca in order to be able to emulate even larger number of qubits. And as a side effect of this project, this is, when you work in research, very often you find results that were unexpected. Okay, and this is a nice example. As a side result of this research activity, apparently, we are on the verge of finding a way to factorize the product of integer numbers in polynomial time by using a theory that has been used also to design of this emulator. So this study is still undergoing, but I don't know if you are aware, but the factorization of prime numbers is the building block of many cryptographic systems. Okay, and so you may think about the huge social impact about this result if confirmed. As another example, something that Alessia was mentioning in her talk is this quantum supercomputer entirely built in Italy. This is a joint, again, project between the University of Naples, the CNR, and Cineca. There is a machine with 25 qubits already available and 60 qubits by the end of the year. This machine has been entirely built in Italy, and as far as I know, is one of the biggest academic quantum computer in Europe. We have a photonic quantum chip on the way as another result. With this type of projects, we were able to write more than 200 publications in the past 2 years of activity. And so this is about mostly academic research. But as you have seen also with the other spokes, one of the missions we've been given in the National Center was to connect research with the industry. So as an example, we have this family of projects we call the innovation projects, which by design, they have to be projects led by industries. And I was surprised when we started working with quantum computing. Quantum computing is a very edge technology. So you may think that there are not many end-user industries interested in experimenting with the quantum computing. But I was surprised that there are 10 projects running on quantum computing, all led by industries. There are 9 private institutions that are cooperating with 8 public institutions, and all of them are in the application domain. So all of these projects, all of the industries are interested in the practical utilization of quantum computing. And there are mainly 4 main application domains. Well, the first domain is simulation, which is probably the most typical usage of quantum computers when you want to do engineering simulations or physics simulations and so on. But there are also many projects in financial sector, fintech technology. There are projects on cybersecurity, and there are projects in the utilities and logistic domains. So these are some of the companies that have been involved. Some of these names you have seen also in the other spokes: Eni, Oil and Gas, Leonardo Defense, Thales, Aerospace, Fincantieri, Naval Industry. I don't want to, we do not have the time to list all of them. Unipol, Intesa are bank and insurance companies in Italy. We have Sogei Engineering, which are, Sogei is a company that provides services to the public administration. Engineering is a consulting company in Italy. So this is an example of this industrial projects. So then we have these external projects. External projects are projects done in cooperation with industries or public institutions which are not members of the center. And again, I was surprised again by the huge number of projects. There are overall 16 projects running, 12 of them with private institutions and with 7 also public institutions involved. And you see here the list of application domains involved. So we have in the pharmaceutical sector, in the artificial intelligence, physics simulation, again, fintech, engineering, utilities again. And then we have 4 projects here focused specifically on the design of hardware and middleware technology for quantum computers. So that's almost all, okay? Because I would like to end my presentation with my vision on on quantum computing, and I want to use an example. All of you are aware of the incredible, let's say, results that artificial intelligence is doing now. So we have a lot of examples of how artificial intelligence is changing society. For instance, ChatGPT, but it's not the only example. But we should keep in mind that the theory behind the artificial intelligence that we have today is more or less the same as the theory of artificial intelligence 10 or 20 years ago. So what really changed is that nowadays we have computing accelerators like GPUs that we have seen also in other spokes. GPUs that allow us to simulate artificial intelligent models with billions of simulated neurons. Okay, so this is the real key factor. Now, I strongly believe that quantum computers have the same disruptive potential. Not today, because the technology is not yet mature, but the potential is there. It could be in 10 years. We will see another revolution, and a revolution which will not affect only artificial intelligence, like with the GPUs, but many, many other research or application domains. So that's all, and thanks for your time.
Question? Okay, if there are no questions, thank you again. So we are come to the end of the session. So thank you to all the speakers. Special thank you to all of you for your participation.